Welcome to a brand new video. We at Biosolve IT are proud to present to you the latest major iteration of SeeSAR version 11. This video is intended to give you, SeeSAR users, a quick overview of the newly added capabilities enabling seamless integration into your SeeSAR-based drug design projects and workflows. SeeSAR 11 is christened Hephaestus after the Greek god of fire, metalworking, stonemasonry, forges, and the art of sculpture. SeeSAR Hephaestus is dedicated to you, the artisans of drug discovery, to help you craft, forge, and sculpt powerful drug molecules against human disease. SeeSAR Hephaestus introduces a variety of new innovations, including covalent docking, the ability to save and restore 3D scenes within SeeSAR projects, additional descriptors to guide your decision making while working with proteins with unknown binding sites, the ability to export 3D models of protein-ligand complexes from SeeSAR to any other mode of presentation, and convenience features which will be explained to you over the course of this video. Despite the inherent complexity of these newly added features, we have worked hard to stay true to the spirit of SeeSAR, which is to keep things fast, visual, and easy. In the remainder of this video, you'll get a walkthrough of these new features in SeeSAR to learn and understand on how to use them best in your own drug design projects. As always, if you would like to skip to individual segments of the video, please use the timeline annotations in the video description below. Let's begin with covalent docking. The docking mode that you're all familiar with has now undergone a facelift. Fundamentally, the buttons for standard and template docking have been redesigned, and a new button that enables the generation of covalently bound poses has been introduced. As long as you have prepared your protein and ligands for covalent docking, the docking run itself requires just a single click on this new button. Now you're probably wondering what really preparing the protein and ligand for covalent docking means. Let's find out, shall we? The simplest means to use the covalent docking functionality in SeeSAR is to start with a covalent protein-ligand complex from the PDB, and as a first step, redock the same ligand to explore the conformational space of the ligand in this binding site. Let's look at this example molecule on screen. A covalent inhibitor of the SARS-CoV-2 main protease recently deposited into the PDB. SeeSAR identifies that this molecule has been extracted from a covalent complex by the presence of this R group or a linker atom. New molecules can therefore be prepared for covalent docking via adding the molecule first to SeeSAR's molecule editor and manually adding these additional R or linker atoms via an improvement to the change element panel of SeeSAR's molecule editor. The positions of existing linker atoms can also be modified by deletion from their original position and adding them subsequently to a different position on the same molecule, in essence creating a new molecule in the process. Molecules that do not contain any of these linker atoms can first be added into the molecule editor, and then new linker atoms can be positioned based on the user's wish, making them suitable for covalent docking. Now let's see how all of this works in SeeSAR. Let's open up SeeSAR 11. We're greeted by the new splash screen with the version number and the Hephaestus logo in the background. Now let's click on the new project and get straight to business. Now that we're in the proteins mode of SeeSAR, let's download our PDB of interest, PDB code 7LYI. And then we see a list of ligands that are given by SeeSAR automatically. The first thing to note here is that one of these ligands has a little eye icon on it, and mouse hovering right on top immediately gives us the information that this ligand is covalently bound, which makes it very clear that this is the ligand that we're looking for, the covalently bound ligand. So let me radio select this and click on the green play button to immediately choose my covalent ligand of interest in this protein. And as a confirmation, the same image that we saw in the slide earlier is also available in the 2D window here, along with the R linker atom present here. In 3D, the linker atom is shown by this light blue R cyan atom represented at the point of covalent attachment on the protein. We do notice that Hyde coronas are displayed on the atoms of the ligand molecule, but an estimate of binding affinity computed by Hyde is not explicitly mentioned here, and these will not be provided for covalent ligands. Just to check, we could right-click and press the Calculate Estimated Affinity button, but only to find that the column is still empty, confirming that for covalent ligands, a Hyde predicted estimated affinity will not be explicitly mentioned, but atomic contributions to the non-covalent affinity will be shown via the display of Hyde coronas. Since our aim here is to learn about covalent docking, the next logical step to do would be to add this molecule to the docking mode and run a docking simulation. But just before we do that, let's do a bunch of housekeeping in terms of the visual settings, just so that we keep only those parts of this protein ligand complex that essentially matter to us. So we're going to delete the secondary structural representation of chains and get rid of all of these water molecules. And now that things look much better, let's right click on the row and add to the docking mode. In the docking mode, something immediately catches our attention. A translucent capsule on the residue in the docking mode is a visual indication that this residue has the potential to be selected as a point for covalent attachment of molecules. A pink capsule indicates that this particular residue has been selected for covalent docking, meaning as long as our docking library contains molecules prepared for covalent docking, that is containing these R linker atoms, they would be successfully covalently docked on this residue. Now all we've left to do is to click on the covalent docking button and see what turns out. And there in a few seconds we have 10 poses of our ligand molecule generated with the same covalent attachment. Once poses have been generated, the quality of individual poses can be analyzed either visually by comparing the Hyde coronas generated on the poses, or by sorting them based on one of the other visual indicators for conformational quality, namely the torsion quality and the intra and intramolecular clash representations. Selected molecules can be further optimized by making full use of all of the lead optimization capabilities that SeeSAR provides via its molecule editor and inspirator modes. Now let's pick one of the best molecules from here based on an indication of the maximum number of Hyde coronas that we see, and take it to the molecule editor to change the position of the linker atom on this molecule. So right click, add this molecule to the molecule editor, and there we see our molecule both in 2D and 3D again. Changing the position of the linker atom on this molecule essentially involves two steps. First, selection of the R linker atom in either 2D or 3D, and deleting this atom by using either the delete key on your keyboard or by using this trash can icon symbolizing delete. So let's delete that, and then find a new position on this molecule to add a linker atom. So I pick an arbitrary atom here, change this to a metal, and add a R linker atom by either hitting the R key on your keyboard or going right up here to the change element panel and clicking on this R button. Once you've done that, click on the green button to save this molecule as a edited, modified version of your original molecule, and we immediately see that a height estimation of affinity is being done on this molecule since it's not covalently attached anymore in the molecule editor per se. And then now we could take this molecule back into the docking mode and run another docking simulation wherein the molecule would be attached to this particular cysteine residue via our newly defined linker position. So that's essentially how you could bring in a molecule without any linker into the molecule editor, add a linker atom to the position of interest, take it to the docking mode, and with one click on the covalent docking button, generate covalently bound poses of your molecule. Moving on, clicking on this pink capsule here will turn it blue, but internally what happens is we switch off the covalent nature of this residue. Now if we try running covalent docking, SeeSAR would throw an error message saying that this binding site has not been prepared for covalent docking. This is a convenient way to check on how molecules bind to this binding site in a non-covalent manner to obtain hints on how the non-covalent properties of these ligands can be optimized. What this teaches us in summary is that a capsule being marked blue means that the residue has been marked for covalent docking but not essentially selected for covalent docking, while the one that is marked pink by clicking on a blue capsule is the one that has been selected for this particular run of covalent docking. And this information is rather critical for the next step that we're gonna do. And that is that we notice in the vicinity of this particular cysteine residue in our binding site, another residue conveniently positioned that can also be a host for covalent ligands, which means that this could also act as a receptor for covalent docking, and that's a methionine residue. So in the following workflow, we're going to see how we could use SeeSAR's protein editor mode to make this methionine residue an additional target for covalent molecules, and then interactively choose between these two residues, the cysteine and the methionine, to perform covalent docking in the docking mode. And for this workflow, let's go ahead and clear the docking mode for now. We do not need any of these molecules here. Let's go back to the protein mode, and first thing, add this protein to the protein editor mode. Okay, now we select our methionine residue to which we'd like to add a linker atom, and to give some perspective on how this looks in the protein, let me shortly switch on the secondary structural representation of the chain. So that's the methionine residue that I want to target. So all I do is change this to a R linker atom, again by simply pressing the R key on the keyboard or going over to the change element panel and pressing the R button. With any edit, we immediately save a new version of this protein, and now send this back into the proteins mode. Select our covalently bound ligand since the binding site is essentially the same. Delete this initial version of the protein since it is not of any use to us now. quickly take this molecule into the binding site mode to confirm that this is still our binding site of interest. And from here, we could now take the ligand molecule to the docking mode. And there we see it. We have two capsules, one pink, which is the selected capsule. So this is the cysteine, which is the capsule that is selected for the residue that is selected for covalent docking. And on the other hand, we have our newly created covalent target, the methionine residue, with the blue capsule, which means it's marked but not selected. So selecting this residue over the cysteine simply involves a click. And now, if I run a docking simulation, all of these molecules would be docked covalently attached to our newly created methionine residue. There we see it. And the cysteine residue here remains open, it's blue, and it's not marked for covalent docking in this case. And this essentially opens up several possibilities. You could find other residues for possible covalent targeting, or you could edit residues in the molecule in the protein editor of SeeSAR and create new versions of your binding site for covalent docking. Or in the extreme case, if you'd loaded a protein that did not have a residue compatible for covalent attachment, you could create this in the protein editor and then perform covalent docking. So we've seen two sides of the same coin. We've seen how to prepare ligand molecules compatible for covalent docking. We've seen how to prepare your protein, especially the residues around the protein's binding site, compatible for covalent docking, and how to interactively switch between different such created residues to perform covalent docking for interactive, visual, and intuitive inspection and prioritization of your molecules using SeeSAR. And with that, we come to the end of the walkthrough of the covalent docking part in SeeSAR Hephaestus. Moving on, we're gonna see the next cool new feature added to SeeSAR Hephaestus, and that is the ability to save and restore 3D scenes from within SeeSAR projects. What this essentially means is that the annotation panels that you will find usually found in molecules have now also been added to proteins, and an extension of the annotation panel can be used to now save, which means capture, and restore captured scenes. So let's see how this works in the tool itself. Let's continue from where we left off with the covalent docking discussion. So let's go back to the proteins mode, and it could be that with the protein, I'd like to get a full overview on where the binding site is relative to the rest of the protein. So I'd like to switch on the binding site representation on this protein. And then this is a good 3D representation that I like. So what I do is go over here, click on the annotation panel, and possibly annotate this. And capture this scene, which means that this 3D setting is stored within the project. Which means I could go back to doing other things. For example, remove the binding site visualization because I want to create a new visualization on the molecule. Namely, that I want to have a zoomed in version of how this molecule looks in its bound state, and then I can create a new visualization that I can capture again by clicking the annotation panel on the molecule. That opens this sticky note. Whether I want to manually annotate my molecule or not is optional, but the moment I click on capture scene, this visual state is essentially stored within the project. And now, at a different point of time, I could choose to go back to the proteins annotation and click on Restore Scene to get the original state of how I'd saved my protein visualization. And similarly, go back to the molecule annotation, and clicking on Restore Scene will then get me back to the state where I left my molecule at. So if I'd like to overwrite this molecule visualization to something else that I prefer, maybe an arbitrary position like this, I'd have to initially delete this scene and capture this scene again, which means that it will be restored in the exact same position that we've captured it. So this greatly enables collaboration, especially when working with multiple molecules like in the docking mode. You could select certain molecules, annotate them as to why you like the docked pose, for example, or why you don't like them, save it in a particular orientation as you prefer, and once you save a SeeSAR project with these information in, your colleague who receives the project for collaboration can retrieve the 3D state in the exact way as you saved it, and then can continue working on the project in a seamless manner. And that's how this feature can be put to practical use. The next additional innovation in SeeSAR 11 has to essentially do with an improvement to the binding site mode of SeeSAR. So here we've added more information to guide your decisions on binding pocket selection, especially if you start with a case where the protein of interest has no known binding sites. So we use the binding site mode and the show unoccupied pockets button in the binding site mode to then use the dog site scorer algorithm to show a list of predicted binding pockets. And so far, the only variables that were given to the user were the pocket ID and the number of residues. We've now greatly improved that to add more descriptors, including a dog site score, which is nothing but a simple score of druggability, the number of hydrogen bond donors and acceptors, the hydrophobicity rated between a scale of 0 to 1, the surface, which is nothing but the solvent accessible surface of the binding pocket, and also the volume of the binding pocket. Let's see how this is done in SeeSAR. For this part of the demonstration, we'd ideally like to start in a clean slate. So I've cleared all molecules and proteins from every other mode that we had so far by going File and New. And now let's reload this protein back into the protein mode. And here make sure to select Do Not Extract the Ligand, because we want to treat this protein as if we had no idea of what its binding site was. With that done, let's move to the binding site mode. And with one click of this button that reads Show or Hide Unoccupied Pockets, we let the dog site scorer run in the background, and in a few seconds we have proposals for binding pockets both in 3D via these colored clouds and corresponding rows of pockets added here. And like we mentioned earlier, now more than just the number of residues to make your judgment from, we have the dog site score, which is a simple score a simple druggability score based on the dog site score algorithm, the number of donors or acceptors, the hydrophobicity, which is in a scale of 0 to 1, which is defined as the ratio of lipophilic pocket heavy atoms to all pocket heavy atoms, the solvent accessible surface, and finally the total volume of the pocket. And all of these columns are sortable, which means you can choose any one of these parameters to make your decisions on selecting binding pockets in case you start with a protein without a definition of a binding site. The next cool new addition to SeeSAR 11 has to do with the ability to export the 3D representation of your protein-ligand complexes into a format that can be loaded by any 3D modeling program or even in PowerPoint. And let's see how we go about that in SeeSAR. And for that, let's load a protein, any arbitrary protein, select a particular ligand and confirm it. And then the definition of our binding site essentially is these residues that form the binding site and the molecule that is attached to it, including all of the crystal waters that make up the binding site. And most importantly, excluding the protein secondary structural representation. So what we could do now is, instead of what we've usually done, if we want to take this representation to a presentation, we'd normally have gone over here to utilities and taken a screenshot, but instead now you can export a 3D scene, which then exports this data in this new file format called GL transmission format. And let me save this here as binding site and save. So what this means, that in its most relatable form of application, what I could do is open up an application like PowerPoint and go over to this insert a 3D model into my presentation. I choose my device, and where I've saved my binding site's 3D representation as a model can be brought into this presentation, as you see here. And this is not a static image now, but a fully rotatable and viewable 3D model. To top this off, we could also probably add some effects, like the one that's commonly seen in the animation segment here. For example, an initial effect could be a transitioned entry or a turntable effect that could demonstrate the full 3D visualization of your protein ligand binding situation and essentially take your presentation to the next level. The final couple of additions to SeeSAR 11 could essentially be grouped as convenience feature. The first of which is the automatic secondary structure visualization that is now introduced in SeeSAR 11, wherein any PDB formatted file, irrespective of secondary structural annotations being written into the file or not, SeeSAR automatically runs the DSSP algorithm in the background to compute and visualize the secondary structures in these proteins. So the image you see on the left is what a homology model produced by a different program was visualized in SeeSAR version 10, and the version on the right is the same protein visualized in SeeSAR 11. And the important fact is that the underlying file itself does not contain this annotation, but it's done on the fly in SeeSAR and visualized successfully. The final improvement to SeeSAR 11 that we're going to discuss as a part of this video is easily one of those things that can be called as a small thing that makes a big change. And the feature essentially is the ability to select multiple molecules from your local machine and drag and drop them in one go into SeeSAR. Although this sounds at the outset as a rather trivial feature, it does save a lot of time when put to actual use. So I've copied around 10 molecules now together, so I've dragged it and I'm just dropping it, and SeeSAR loads these molecules, does all of the calculations in the background, and this essentially works for all modes that work with molecules. So the analyzer, the inspirator, the molecule editor, and the docking modes. With that, we've come to the very end of all of the new additions to SeeSAR 11, codenamed Hephaestus. We look forward to you using SeeSAR 11, benefiting from all of these newly added innovations to the major version. We hope you've enjoyed this video. We thank you for your attention. Stay safe, stay healthy, and goodbye.